simulating the magnetic train, Maglev. Hello everyone, I hope you are doing great. In my latest video, I talked about some experiment, AA battery with magnets, and also combination of simulation with experiments of that. And I hope you guys support me, subscribe to my channel, share my channel to your friends, and see my video and help me to monetize in YouTube channel. Let's get started. Before starting, I would like to talk about the magnetic train, from the simple experiment to real magnetic train that maybe you saw in your countries or in news. Let's get started. Here at the first experiment, we can see an AA battery with 3 neodymium magnets that attach to the two ends of that, and by placing these magnets and battery to the coil of copper wire, bare copper wire, we can see that this system can rapidly move from this coil. Let's see that. Okay, you can see that. For doing this experiment, the important thing that you wrap a bundle of bare copper wires around a rotating motor to form a tightly wound uniform coil, and also consider this fact that the copper wire must be bare without any insulation cover on that. Okay, also in this example and in this experiment, you can see AA battery with neodymium magnets at both ends that cause the rotational motion as long as battery has charge. Okay, by connecting the coil, and in another experiment, we can see that two separate batteries can be moved along this coil, that no interaction with to these batteries to attract them, and also it can be useful for future experiment. In this new experiment, I provided several twisted copper coils that used to see whether the battery and magnet devices can pass through them, and to determine what factor influence their power and speed. Okay, we can see the higher battery's power, the faster device For understanding the physics, let's detail the explanation. At first, we have a magnetic field from the neodymium magnets. The neodymium magnet at the ends of the battery create a strong magnetic field. The magnetic field lines run from the north pole of one magnet to the south pole of the other, passing through the battery and the surrounding space. Electric current in the copper coil. When the battery is connected to the copper coil, an electric current flows through the coil, the direction of the current depends on the orientation of the battery, positive and negative terminals. Here we have a Lorentz force. The interaction between the magnetic field from the neodymium magnets and the electric current in the Cooper coil generates a force that we call Lorentz force, that's given by F equal to IL cross B. That F is force, I is the current, and L is the length vector of the wire in the direction of the current, and B is magnetic field. Motion of the system. The Lorentz force causes the system, battery plus magnets, to move through the coil. The direction of motion is determined by the right-hand rule. And also we have a Faraday law for induction. As a system moves through the coil, the change in magnetic flux through the coil induces an electromotive force, EMF, according to the Faraday law. That is, E is equal to minus d phi, that is equal to this related equation. The phi is magnetic flux through the coil, and d phi b dt, it's rate of change magnetic flux. Rapid motion. The system moves rapidly because the neodymium magnets provide a strong magnetic field and increasing the Lorentz force. The low resistance of the Cooper coil allows a high current to follow, further increasing the force. The lightweight nature of the system, battery plus magnets, allow it to accelerate quickly. And we can conclude the rapid motion of the system through the Cooper coil is due to the Lorentz force generated by the interaction between the electric current in the coil and the magnetic field of neodymium magnets. Faraday's law of induction also plays a role by inducting an EMF that sustains the current and motion. This setup is a simple demonstration of how electric energy can be converted into mechanical motion using electromagnetic principle. Okay. Here I provide a comparison between a very fast mechanical mini car and simple electromagnetic train experiment. You can see a comparison of a speed between a small mechanical car of the same size as this device of magnetic and battery, which includes that is presented here. The results show that it can be concluded the speed of magnetic train is faster than mechanical car. For estimation of the speed, we can see this equation, and the velocity of v of the moving system depends on the balance between driving and resistive force. M dv divided by dt equal to ILB minus F drag. The F drag is due to the resistive force like air resistance and internal eddy currents. At a steady speed Vs, we can approximate that ILB equal to F drag. Since drag forces in air are low, the system achieves a high velocity quickly. Okay. These experiments have led to the conception of magnetic levitation, Maglev trains, that we want to investigate of them. In this new experiment, using a standard short base holder, as can be observed, it is not possible to keep two analogous poles of a magnet in a repulsive state stationary, as they are ejected outward. To solve this problem, we use a holder with a taller base. Let me show you. We can use a taller holder. And additionally, using a small locomotive's car here is not suitable, as it leads to unstable conditions on the turns. Therefore, a larger locomotive should be used instead of that. You can see the schematic. By applying a small amount of force, this magnetic train system starts to move, and the notable point is the levitating nature of this system. In this section, we connect a magnetic coil to the power supply and attach it to the rail that allows us to send pulses to the magnetic train, which increases its speed. You can see the power of and by pulsing you can see the speed of magnetic train, and by increasing the number of Cooper coils, the speed of the magnetic train can be increased. Now we can investigate the real magnetic train maglev.
More expensive to build, cannot use existing infrastructure, and use more energy at high speeds. Maglev trains have set several speed records. The train speed record of 603 km per hour, 375 miles per hour, was set by the experimental Japanese L0 series maglev in 2015. From 2002 until 2018 by attraction to a ferromagnetic, usually steel, rail, while electromagnets, attached to the train, are oriented toward the rail from below. The system is typically arranged on a series of C-shaped arms, with the upper portion of the arm attached to the vehicle, and the lower inside edge containing the magnets. The rail is situated inside the C, which only work at a minimum speed of about 30 km per hour. This eliminates the need for a separate low-speed suspension system, and can simplify track layout. On the downside, the dynamic instability demands fine track tolerances, which can offset this advantage. Eric Lathwaite was concerned that to meet required tolerances, the gap between magnets and rail would have to be increased to the point where the magnets would be unreasonably large. In practice, this problem was addressed through improved feedback systems, which support the required tolerances. Air gap and energy efficiency can be improved by using the so-called hybrid electromagnetic suspension, HEMS, where the main levitation force is generated by permanent magnets, while the electromagnet controls the air gap, what is called electropermanent magnets. Ideally, it would take negligible power to stabilize the suspension, and in practice the power requirement is less than it would be if the entire suspension force were provided by electromagnets alone. Electrodynamic suspension, EDS. In electrodynamic suspension, EDS, both the guideway and the train exert a magnetic field, and the train is levitated by the repulsive and attractive force between these magnetic fields. In some configurations, the train can be levitated only by repulsive force. In the early stages of maglev development at the Miyazaki test track, a purely repulsive system was used instead of the later repulsive and attractive EDS system. The magnetic field is produced either by superconducting magnets, as in JR Maglev, or by an array of permanent magnets, as in Indictrack. The repulsive and attractive force in the track is created by an induced magnetic field in wires or other conducting strips in the track. A major advantage of EDS maglev systems is that they are dynamically stable. Changes in distance between the track and the magnets create strong forces to return the system to its original position. In addition, the attractive force varies in the opposite manner, providing the same adjustment effects. No active feedback control is needed. However, at slow speeds, the current induced in these coils and the resultant magnetic flux is not large enough to levitate the train. For this reason, the train must have wheels or some other form of landing gear to support the train until it reaches takeoff speed. Since a train may stop at any location, due to equipment problems for instance, the entire track must be able to support both low and high-speed operation. Another downside is that the EDS system naturally creates a field in the track in front and to the rear of the lift magnets, which acts against the magnets and creates magnetic drag. This is generally only a concern at low speeds, and is one of the reasons why JR abandoned a purely repulsive system and adopted the sidewall levitation system. At higher speeds other modes of drag dominate. The drag force can be used to the electrodynamic system's advantage, however, as it creates a varying force in the rails that can be used as a reactionary system to drive the train, without the need for a separate reaction plate, as in most linear motor systems. Lathwaite led development of such transverse flux systems at his Imperial College laboratory. Alternatively, propulsion coils on the guideway are used to exert a force on the magnets in the train and make the train move forward. The propulsion coils that exert a force on the train are effectively a linear motor. An alternating current through the coils generates a continuously varying magnetic field that moves forward along the track. The frequency of the alternating current is synchronized to match the speed of the train. The offset between the field exerted by magnets on the train and the applied field creates a force moving the train forward.
Here, I want to show you how we can simulate electrodynamic levitation device. Here, the device consists of a circular aluminum plate placed above two cylindrical concentric coils carrying sinusoidal currents in opposite directions. The time-varying magnetic field created by the coils induced eddy currents in the plate, which in turn give rise to repulsive force sufficient to make the plate levitate at a certain height above the coil. The application models the dynamics of the plate in the time domain from when the coils are energized to the end of the transient after 1.7 second. The results, and in particular the position of the plate, are compared with the experimental data available from the TEM problem specification. Here we can see the model. I provided a magnetic field MF, and by adding domains free space in the outside of copper and aluminium, and you can see the coil 1 and coil 2 with the number of turns, coil wire conductivity, and cross-section area of coil. The boundaries are considered via axial symmetric and magnetic insulation. The geometry was based on coil 1 with a width of 28 millimeter and height of 52 millimeter, and I just selected. And coil 2, it's with the widths of 15 millimeter and 52 millimeter height in the base position of center 87.5 millimeter and minus 26 in the Z direction. And rectangle 3, that is consist of 3 layer with the related thickness, as you can see, and rectangle 4 and rectangle 5. Here a copper from the material library, but just by clicking from material library I add the copper in these two sections the mu r and epsilon was considered 1, and the aluminum as mu r1 and sigma with the related parameter here 3.4 E7 Siemens per meter. And I choose a moving mesh to show the disk of aluminum how levitate on the top of the two coils. Okay, and also I add global ODE by writing this equation, and this equation that comes from this related equation, which is from the Newton laws, and a study of time dependent in the range of 0 to 1.7 with a step size of 0.01, and after simulation in nearly 4 minutes you can see the current density, and I can just animate that. The current density, and also let me show you again. You can see that is levitating on the top surface of the coils, and it can be used for simulating the magnetic train, Maglev, and the other device that is that has levitation on it, and understand what the physics of that and how it can works. Thank you for watching this video. I hope you subscribe to my channel, share my channel to your friend. Please see all of my videos, like my videos, help me to monetize my channel, and big thanks for all of you. Have a good time, take care, goodbye.